Okay, so we haven't really talked about learning. I think we touched a bit on this core node dual play, and to try to sort of give you an idea what to mean by learning. Okay, so what do mean? How can we find equilibria or find some of equilibrium in the equilibrium set? So you can consider this kind of dynamics like a best response dynamics as kind of learning, because each time you have observation, you have some data, additional data observed, like for example, what are the play the other opponents did, and then sort of you do the iteration, eventually coming with that convert to certain thing, certain joint profile, which hopefully is one of the equilibria. So that's basically the learning is about. So today we're going to talk about, in fact, a good quotation mark here is that, strictly speaking, today the solution we're doing here is not about learning, it's about solving it, right? Not necessarily to be using learning technique. The learning is really about sort of say, based on the experience in the past, and you were able to improve that based on these, those experience that you had. But solving could be different. Is that I already know everything. I know all this information. I just want to sort of, find my solution. Okay, I don't really have that kind of iteration in order to get that. So I think that's the difference between solving and learning. Okay, this is just not necessarily strictly like a definition between solving and learning, but it's just a way that I looking at the difference between them, because there's no like a clear definition of this. Some of the solving have to rely kind of learning, but also the other way around. But typically in the optimization community, people tend to say, solving solver. Is precisely because of that. Is that you actually know everything, like a linear programmer. You basically linear programming because have that, all these parameters, and you try to sort of solve it. And but of course, you can actually turn into a learning algorithms that each time you fetch some data, then you could gradually improve that. So that's the difference. And also, if you have time, and then I would encourage you to really looking at this exercise. Really, this is show this, and in different sort of setting, then you might have a different conclusion. In different setting of game, you might have conclusion. This is sort of a bi-level step-work kind of setting of the same problem, dual play problem. For example, say if we break the symmetry between these two players. Let's say assume one of them is leading, one of them follow. So in other words, as a leader has the understanding, or leader would start first, and also they have understanding of the followers' policy. In other words, they know exactly what the kind of policy the follower has. Then this leader can, based on that information, to optimize it. Whereas the followers can also optimize is based on the observation from the leader, because the leader starts first. Then they have a sort of action review to the follower, and the follower, based on that sort of actions, and can do the best response. And because this kind of asymmetric kind of representation of the problem, therefore, you might have a different sort of conclusion. That's just to see how it goes. So we're going to have a similar setting as before, and then this utility of then would be quadratic. Then the difference though is that this form 1 would start first. Assume that they are leader, right? And let's say form 2 is a pure strategy, and this would depend on sort of mapping from Q1 to Q2. So in other words, you have Q2, which is best response to Q1. whereas form 1 is that they would decide what this what the quantity of the product they're going to produce in the very beginning, because they start first, they have no observation whatsoever about what form 2's action, but the form 2 has the observation about Q1 because that form 1 start first, and then since form 2 moves last, we first find that the optimal Q2 as a function of Q1. Suppose that you have this optimal Q2 function, which is the best response, right? Given any Q1 you've got. So how do you actually get that? So you can easily get that because you can write down this utility function as before, right? Suppose that you know this Q1, then you basically take a derivative of Q2, you find that. So then you can actually write down this. So let's put it as like a optimal one. Given any sort of a Q1 quantity to produce from form 1, the best response of the Q2 would be A minus Q1 minus A divided by 2. Okay, so given the fact that this has become the policy, right? Policy or strategy of form 2. Given the fact that leader would know everything about this game, therefore they know this sort of Q2 function, and they basically could replace this Q2 function in their utility function, right? And then you can actually write it down this as this, and then can take a derivative. Therefore, you can solve for Q1. You can see here the result is this: the Q1, Q2 are not symmetric anymore, right? You can see that actually Q1 can produce a bit more of their product than Q2 because they had advantage, right? They can advantage on that. So this basically shows the symmetry between these two players, therefore has some consciousness of that. So the reason I just give you this formulation is that it's not always the game is played in the symmetry, right? It could be some cases that some player or user start first and others follow, and they might have, in terms of information received, might be different. Also, dependency might be different, therefore have some consequences. And for example, we were talking about football. So I think football maybe we can use some kind of this bi-level or stackable kind of model, really to model these players, because all these players are not necessarily to be symmetric. In other words, they're not necessarily to equipped with a same capability, right? They're not necessarily to contain all the information. So I think it would be a very interesting way to model that. So I think just try to summarize what we have studied so far. We got started game theory, and mostly we didn't really talk about the competition too much, right? Apart from the Connors case, and so really the question is that how can we actually compute Nash equilibria or one of equilibrium find? And it turned out, in fact, find this Nash equilibria extremely difficult, right? But it only happens, it's only possible if you have a very simple case. So we were going to look at the two-player, two-action game, as it's very simple, and we'll go back to then this two-player zero-sum, okay, normal phone game. So zero-sum means that there's certain sort of a reward structure, and then we will go back. After that, we were looking at one of the practical algorithm called Look-Hawthorne algorithm, and to really dealing with the general sum normal game, but it's with some limitation as well. So this is Nash equilibrium. I think we already explained. We already proved the Nash equilibrium. It's basically show for any finite game the existence of the mixture strategy, mixture Nash strategy. So let's looking at this min-max theorem. Okay, so this min-max theorem, in fact, even earlier than Nash theory, because Nash theory was sort of developed 50s, but from von Neumann, he was one of these pioneers study game theory, and provide this modern treatment on that. So one of the important theory was min-max theorem, because at the time he was studying this sort of a card game, right? In the card game, let's say you have two players. One is try to win, another fight each other, right? And both of them try to win. So you can actually write it down is that you got this value, right? Then of the game, like one of them try to maximize, another try to minimize it. So this is very nice or simple case, because that kind of reward structure would allow this von Neumann develop a theorem and would provide a simple solution for that. Okay, let's just clarify some of the definition. So in this zero-sum game, then we have an opportunity basically to define this value of the game, because then you could either from this player one's perspective who try to maximize it, right, or players two perspective who try to minimize it, and then therefore define the value of the game, because this reward three gonna be adding them together gonna be zero. So when you're looking at the player one's perspective, you already get the picture of the game already. So let's look at, suppose we have this player one, player two, and two action. How can we sort of do the calculation? So this is sort of a zero sum in the sense that if I win, you lose, right? So if I get this -2 sort of a payoff, you get +2 payoff. If I get -3, you got the -3. So it's got a certain structure of that. Let's just talking that this you got this two player, right? Two player, two action. So this game has no pure strategy Nash equilibrium. Suppose that in some cases, let's also suppose that if they don't have a pure Nash, or let's focus on figure out how can we get this mixed strategy Nash equilibrium. So the condition is that it is a mixed strategy. Okay, and how can we find it? I think we briefly expanded one of the idea is that I choosing my strategy is in such a way the opponent would make no difference between their actions, and therefore they could allow to choosing a mixed strategy. Otherwise, equilibrium wouldn't be a mixed strategy, because if when I choosing my probability of play, then from another player's perspective, is one of actions higher value than others, then they will always choosing that action. Therefore, their action wouldn't be pure strategy. Wouldn't be mixed strategy. Therefore, that whatever I choosing, there wouldn't be a mixed strategy Nash equilibrium. So that's the intuition behind it. So let's looking at this reward first. So suppose we define the x1 be the probability that player one play action roll one. So basically x1 is a probability they're gonna play this. Action 2 is 1, then y1, y2. Okay, if you divide this, we can actually write it down. These yes. So this could be 1 minus 1 y1. Okay, this x2 is the x1 minus x2. So you can then to write about the expected payoff for player one, right? So because this is looking at all this, and then looking at the expected value of that is based on the probability of the play. And you can also write this expected payoff for player two as well. So as I said that if player two is selecting y1, so that player one gets higher utility by playing roll one, instead of row 2, then player 1 will always choosing row 1, as I said. So they have to choosing, player 2 has to choosing y1 in such a way the player 2 would make no difference between choosing row 1 and row 2. What this means is that you can calculate this, okay? This is expected payoff for player 1 if you're choosing row 1. This is expected payoff for player 1 if they play row 2. We need to make sure these two would be the same, right? And when we're choosing this suitable y, it's because of I would make no difference between this row 1, row 2. So make sure player 2 would also choosing a mixed strategy, right? Otherwise, they wouldn't choosing the sort of mixed strategy as equilibrium. So equally, same thing. That's when player 1 choosing, their mixed strategy. Well, they need to also make sure the player 2 would make no difference between column 1, column 2. So we can do that as well, and then for 2 equations, 2 variables, and we can solve it. So we can solve it. So that basically, so in that 2-person zero-sum game, then you can always find a way to do that. Not necessarily to be zero-sum, but in fact, general sum. As long as it's a 2-person, 2 action, you can use the same trick to do that. So here I was using this zero-sum is just to illustrate the value of the game. The value of the game is basically the one who want to maximize it. For example, you can say, you can calculate that based on this based on this strategy, equilibrium strategy, based on this Nash equilibrium strategy, and then you could calculate expected payoff for one of pair. In this case, you can choosing the one has a positive value and consider this as a value of the game. So in this case, it's not necessary to be positive value. Yeah. So here. So opposite. So you can choosing the positive one as the value of the game, or the one has a maximize it as a value of the game. So this is sort of you could consider this, by the way, in terms of formula as a max and min, is that you can consider, this is a max, right? This is sort of minimized, right? This is the max, this is a minimized, because they are, opposite. So this give you a simple exercise to make sure you understand that. If you were given this normal form game, how can you calculate the Nash equilibrium and also the value of the game?